Welcome to my channel Supraja's Technopedia, and the course title is Digital Signal Process and Architecture, which is taught by me Devi Supraja, Assistant Professor. Okay, so before going to the actual content, well, just give a glance to your previous lecture. So what we have discussed in your previous lecture? Introduction to your digital signal processor, need for your digital signal processor, next advantages, applications of your DSP, next about your DFT, FFT and difference between your general purpose processor with your digital signal processor. So here in today's content we'll discuss about your number formats and the need for your number formats fixed point representation. So this is an overview of your today's lecture, which includes your introduction to introduction to number formats, fixed point format, double precision fixed point format, examples of fixed point format. So, introduction to your number formats. So, in any digital signal or your DSP signal, the signals are represented in terms of your numbers, which is your mathematical form. Okay. So, from your input to your output between any different processing stages and number of different processing stages we will deal with your numbers in order to process your signal. So for example, if you take your in order to realize your digital filters of your IAR and your FER filters, we require numbers in order to specify your coefficient. As if you see in your IAR as well as your FER filters, we need a constant which is called as your number, width and delay element as well as your addition block in order to get your input as well as your output. Okay, so in the digital computers are very prominent in order to store as well as your recall the numbers. Unfortunately, this process isn't without error. So, for example, if your computer want to store the number as 1.41421356, but it will do its best in order to store the closest number and it can represent it with your 1.41241421354. So in some cases this might become a big error, or else this can be negligible. So if this becomes a disaster, what happens? We'll check. So another illustration, if you see a normal addition with your two integer numbers, how this will add. So for example, 1 and 0.400001. We would like to add these two numbers, and so the answer will be 1.400001. But the computer replies with 1. So an understanding of how these computers will store and manipulate your numbers will solve your correct problem. So these problems will be eradicated by using a fixed number of bits in order to store each number. Usually it will be stored with your bit representations, either it may be 4 bit, 8 bit, 16 bit, 32 bit or 64 bit. For example, consider the case where your 8 bits are used to store the values of your variable. Since there are 2 power of 8, which gives your 256 possible patterns, and the variable that can only take your 256 different values will have your different pattern recognitions. So each 256-bit patterns might represent the integers from your 0 to 255, 1 to 256 if it is unsigned. If it is signed, then it can be represented with your minus 127 to your 128, etc. But the most unusual scheme, which is also an exponential, in order to represent your 256-bit numbers will be given as your 10 power of 0, 10 power of 1 and so on, so up to your 10 power of 255-bit pattern recognitions or representations. Okay, so in order to access each and every data, what the value or yeah, what each value bit pattern represents. This is usually provided with an algorithm or formula in order to convert between the represented value as well as your corresponding bit. So there are many encoding schemes which are possible, but only there are two general purpose or a generalized formats in order to solve this problem. So what are they? Fixed point as well as your floating point. So your fixed point will deals with your integer numbers and your floating point will deals with your real numbers. Okay. So fixed point representation. The simplest scheme of your number representation is your fixed point representation. In digits allotted for your integer part as well as your fraction part, both are fixed, and your binary point, the position of your binary point will also be fixed in your fixed point representation. So if you want to represent two large or your two small numbers, it will be difficult to represent it as the number as your binary point position is fixed in your signed part as well as your I mean integer part as well as your fraction part. So the number is represented as an integer or fraction using a fixed number of bits. So the end bit fixed point in signed integer will be given as minus 2 power of n minus 1 to your 2 power of n minus 1. It's the range of your n bit fixed point signed integer. So where your s represents the sign of the numbers, if it is 0 it will represent your positive numbers, and if it is 1 it represents your negative numbers. So this is your fixed point integer format, how it will be implied. So this is the position of your binary point and it will be fixed in your integer format, whereas your range will be minus of 2 power of n minus 1 to your plus 2 power of n minus 1, which tells or your which gives your where your n is your bit. Okay. So next format is your fixed point fraction format. So a fraction can also be represented using a fixed number of points with an fixed binary point position after your MSB bit. So a bit fixed sign fraction representation is as shown below. So this is your fixed point fraction format, which is given as x equal to minus s into 2 power of 0 plus b minus 1 into 2 power of minus 1 plus b minus 2 into 2 power of minus 2 plus so on up to your p of minus of n minus 1 into 2 power of minus of n minus 1. So this represents about your fixed point represent in order to represent your signed fractions. So in DSP implementations, multiplication of these integers will also produce small number of bits, and in an even to fixed number of available bits, it may create wraparound. So this wraparound generates the most negative number after the positive number and vice versa. So this problem can be tackled by using a fractional representation, and how your two fractions are multiplied, then the result will also be a fraction. So the resulting fraction may use the same number of bits as the original fractions by discarding your LS base. So this is your example of your. So what is the range of your fixed point representation? What is the range of your numbers that can be represented in a fixed point format using 16 bits? The numbers are treated as signed integers and your signed fraction. So what is the range for your signed integers? It is minus 2 power of your n minus 1 to your 2 power of n minus 1 of minus 1. So as your n is 16 bit, what will be the answer? Minus 2 power of 15, 16 minus 1, which gives you 50, to plus 2 power of 16 minus 1 of your minus 1. So the range will be your 32,768 minus to your positive 32,767. So if it is about your range of fractions, then that can be determined by substituting your n equal to 16 in your equation 2, which is given as your minus 1 to your plus 1 minus 2 power of minus 15, which gives here minus 1 2 plus 0.496948. So this is about your fixed point representation. So double precision fixed point format. So in order to increase your range of numbers that can be represented in your fixed point, there is a one more best approaching method, which is in double precision fixed point format in order to increase its size. So if the size is double, the range of numbers so increases substantially will increase, and it will still use a fixed point format, and it is also called as a double precision fixed point format. So it requires double the storage for the same data, and may need double the number of access for the same size of your data bus of your DSP device.